Okay. Yes, please.
Welcome to the, the computer security seminar from Purdue University. Um, our speaker today is Raghib Hassan from the University of Illinois. He will speak on fake Picassos, tampered history, and digital forgery, uh, protecting the genealogy of bits with secure provenance. Raghib.
Good afternoon, everyone. My name is Raghib Hassan, and I apologize for the really long talk title, but I found out that having a fun talk title always catches the interest of the paper reviewers as well as the audience. Anyway, I'm from the University of Illinois at Urbana-Champaign, and my advisor is Professor Marianne Winslet of Illinois, and I'm also co-advised by Professor Radu Saun of Stony Brook, who incidentally is an alumnus of Purdue as well as CERIAS. Okay, so today I'm going to talk about how we can protect the history of data. But before we go on to the details, let's first play a game. The name of the game is Can You Spot the Fake? And you will be playing the game. So here on this screen, you can see two paintings. One of them is a genuine Picasso worth millions and millions of dollars. The other one is a complete fake. Your task here as the player is to find out which one is the fake Picasso and which one is the real. Now, I'm not really an art connoisseur, so whenever I look at these paintings, all I see is two women with horribly contorted faces suffering some intense pain. But I hope here someone among you will be an art connoisseur and will be able to understand the inner beauty of the painting. So let's begin. How many of you think that the one on the left, that is my left, is the fake one? How many? Okay, 1, 2, 3, 4. Okay. And how many things the one on this one, the one on your right, is the fake one? Okay, 1, 2, 3, 4. Fortunately, you picked the wrong answer because the one on the left of the screen is one of the most expensive paintings in the world. It's called Dora Maar au Cat, which means Dora Maar, which was Picasso's friend, and her cat. If you look closely, you'll see the small cat on her right shoulder here. And in 2006, this was sold an auction for $101 million. The one on the right, unfortunately, is a complete fake. It was listed in eBay, and promptly eBay removed this listing. It's worth nothing. So now the question is, if you have, even in this economy, if you have millions of dollars available to buy paintings, how do you know that you are not buying the real, but buying a fake? How do you know that? So there are many techniques of authenticating art, but among the most commonly used ones, there is the use of provenance records. So what exactly is provenance? The provenance record of an object is a record of the lineage of the object, where the object came from, how it was created, how it was transferred, all the way to the current owner. By looking at this history of art, paintings, and other artifacts, people can make an informed decision about whether they can trust that this is genuine. And this is a widely used concept in art, archaeology, and archives. It's even called the first fundamental principle of archiving. And here you see yet another real painting from Picasso. It's in the Museum of Modern Art. And if you go to their website, you can just pick up this, the provenance record of this painting, which shows when Picasso painted it and how it was sold and bought and sold and exhibited all the way up to the current owner, the Museum of Modern Art. Here's another example of the provenance of a book. Here's a Bible, and as this Bible changed hands, people put their signature names on the left side of the page. So at the end of the day, we ended up with a nice chronological sequence of the owners of this Bible. From the world of physical artifacts, let's now move back to the digital world, the world we as computer scientists live in. And in the digital world, our life is now totally dependent on the use of digital data. You use email, you get documents from others, your documents are stored in databases, passed around the halfway across the globe, and so on. And today, data has also become our most important asset. Money is not important, data. And the use of data is now most important for us as individuals as well as companies. And now the difference with the past is that now that we have all this data in electronic form, this gets passed along a lot. So data is generated by different people, processed by different people, and transmitted between different systems and different storage places. And now, unlike physical storage of data or physical methods of storing data, such as clay tablets or paper or papyrus, things are different now. Because things are stored digitally, now it's really easy for people to change or tamper with a large amount of data within a very short time. In the past, it would be difficult for a single forger to go into an archive and modify thousands of files within just 10 minutes. But now, because they can issue just a query to a database or send a script, run a script, they can modify a large amount of data, large volume of data within a very short time. So in this highly distributed world of data, how do we know that the data we get is correct and it came from the correct persons and it came through the correct channels? How do we trust the data we get from others? So this is the problem, and one nice solution would be to know the history of the data. If we could know how the data was created, processed, transmitted, if you can know the entire life cycle of data, then we can make an informed decision about whether we can trust it or not. That's why we need provenance, data provenance, and provenance which records the entire life history of data. Now, what exactly is data provenance? People have defined it in a lot of different ways. There's a nice survey on provenance by Yokesh Simhan, and there he shows the different types of definitions of data provenance. It has been defined as the origin or the lineage of the data, where the data originated from. And then it has also been defined as the transformation that create data at each stage of its life. And people have also defined it in terms of workflows, the workflow stages that process data. And finally, the derivation history of a value, derivation history of a data object from original value to the final one. What's the use of provenance these days? Well, in the past, provenance used to be used by scientists for different purposes. And even today, scientists are the biggest consumers of provenance. And they use provenance for a number of different purposes. A big concern among scientists is the source of their data, because today's world, scientists collaborate a lot and they exchange data. Now, the output you generate from an experiment would depend on the quality of your input. So that's why it's important to know the source of the data set you are using. And then it can also serve as a replication recipe. If you want to repeat the experiment, then if the final result contained a recipe of how it was created, then you can recreate the experiment. This also can be used for attribution, so that you can know that which person wrote a particular line in a database, or maybe in an article in Wikipedia, and so on. And finally, this has been more increasingly used for audit trails. So if you have electronic voting, or if you have electronic records of business and financial transactions, then provenance, there's the history of that documents is being used to keep or to help with auditing at a later time. So here's an awfully big chart with really small fonts that will annoy you, but you don't have to read the entire chart. Just look at the top line if it's visible there, I hope. So you'll see here a lot of different systems for provenance, and There's the Chimera, Migrate for biology, CMCS for chemistry, and so on. This is a chart from 2005. So by this time, there are a lot of new systems. This is a chart from Simhan's survey paper. So what was the common theme of all those systems? Well, they are all scientific computing systems. They are all used by scientists. And scientists, like good old Einstein here, trust people. They generally are concerned with bigger problems like how to collect provenance, how to annotate provenance, how to store it, and these kind of problems. But if you want to use provenance for our everyday lives, if you want to use provenance for cash register data, financial transaction, bank information, and so on, in those scenarios, the situation is different because here money is involved and money is the root of all evil, so it brings out the evil in the people, and people would have a lot of incentive to tamper with data in those areas. So the previous research, which nicely covers provenance collection, annotation, and other issues, do not really focus on security of provenance, but unless we can make sure that the data provenance itself is correctly recorded and correctly transmitted, we cannot use it for any useful purposes. So to use provenance for anything, we need to have provenance of provenance, that is a way of securing the integrity of provenance. Since I'm from the Illinois, the land of Lincoln, I'll just bring up Abraham Lincoln and a quote from him who said, "History is not history unless it is the truth." So what exactly do we mean by secure provenance? By provenance, we mean that we want to prevent undetectable history rewrites. That is, we want to prevent people from going back in time and change things that have happened in the past. So that's our first goal. We want to prevent undetectable modification of history so that no one can insert fake events, remove genuine events from a document's provenance, and no one can deny their own actions. At the same time, inevitably, there are confidentiality issues where we have to make sure that the provenance information itself is confidential, or we can have it selective confidentiality so that we reveal that information to only the trusted people but not the untrusted people. So here's the threat model we consider in this scenario. In this threat model, we have users like Alice, Bob, and Charlie who edit documents. Now, here there are two things. So I said users edit documents on their machines. That means these documents get passed around between users, and when someone edits a document, it's completely under their control. A log of each user's modification is made, and that log is stored in a provenance entry. And as the document is passed around, these provenance entries keep getting added to the document and so on. And a chronologically ordered sequence of these entries form the provenance chain of the document. Now, there are auditors. In our scheme, we assume that there are multiple auditors in an organization, and they're semi-trusted. I say semi-trusted because there might be many auditors, and you don't trust the auditors, all of them at the same level. You might trust them for your regular data, regular activities, but not for your sensitive information and so on. So only all the auditors can verify the integrity of the chain, but only certain auditors can read each entry. And they can verify integrity and read entry. And finally, we have adversaries. Now, the adversaries are not someone who came from the outside. In our model, we assume that even the insiders can turn into adversaries. And then they can try to tamper with history. They can try to add or remove history entries. They can collude with others to remove or add entries. And finally, they can swap the provenance chain from one document with another document. So these are the different types of attacks that can happen, and these attacks can be done even by insiders with complete access to the data. So what exactly can we guarantee in this scenario? In this scenario, we say that the adversary has the provenance chain. The adversary has the date document itself. So basically, they can, if they want, they can invent history. So what the guarantee we want to provide is plausible history. That is, we want to make sure that, well, let me first define what plausible history is. Plausible history is if we record all the events happening to a document that takes it from its initial version to its final version, that record is a plausible history of the document. So here's an example. Suppose we have this initial version of the document, then someone makes some changes. We have this new version, and again it's a new version, and then someone undoes this thing and goes back to this second version, and then branches off from there to this another final version. So at the end of the day, we have this final version of the document, and it can have two different histories that are totally plausible. So one is this path from the root to this final node, and the other one which takes this loop and comes to this final version. So each of these things that could have brought the document from its original version to its final state is a plausible history for the document. And there might be multiple plausible histories of the document, and one attack could be by an adversary could be to remove all the history and then invent a fake history indicated by the red circle here and include that in the final version. So what exactly do we want to achieve here? We want to achieve this goal. Where if someone presents you with a document and its history, we want to make sure that you can check it for plausibility, and you can check if this history could have happened to the document. So that's our goal. If someone messes up with the history, if we check the history and say if it could have happened, and if there are any tampering activities, we can detect that. But what's the forger's goal? The forger also wants to tamper with the document, and his goal, actually the particular scenario we address in this problem is the scenario where the forger gains by creating a fake history involving honest users. Let me give an example. Suppose that this forger has this fake Prada bag. Pradas are really costly bags, cost thousands of dollars. But there are cheap knockoffs, and suppose this forger has this fake Prada bag, which retail price is just $50, but he wants to pass this off as a real Prada bag. So what he will do? He gains here by pretending that this is a real Prada bag, and by producing a provenance or a plausible history of the bag that shows it came through the right supply chain, through the Prada distributor, real Prada distributors who are honest. The adversary won't gain anything if he does the reverse, right? If he takes a real Prada bag with its real provenance chain and then replaces it with his fake provenance chain involving himself and maybe some of his friends, he doesn't gain anything. In our work, we address this particular scenario where an adversary's goal is to modify history involving honest users. Our goal is to prevent him from modifying history like that. So there's been some previous work on integrity assurances. For example, we have source code repositories such as CERIAS, Subversion, Monotone, GIT, and so on. And that, in some sense, have some sort of signature mechanisms to protect the integrity of each commit. However, you see, most of these work in a centralized model. You have a centralized repository, you check in files, check out files, and the repository does the signatures. So at the end of the day, if you want to see some version history and verify it, you trust the centralized repository signatures. Now there are some versions of these repositories which are claimed to be distributed, such as Monotone, but even then, those systems have a logically centralized repository model. They use a check-in and check-out model. But in real life, we don't process documents that way. In most business workflows, you process something and you process a report and then pass the report to your manager and so on. So we cannot just take that solution and apply to mobile documents like this. Then there are file systems with integrity assurances such as Sunder, Passes, TCFS, And if you put a file in such a file system, and later you can audit the entire history of this file system. But you can do that as long as the file stays in that file system, or maybe transferred to yet another sender or other trusted file system. We cannot carry this integrity verification properties across systems. As we exchange this document between or among a lot of different users, we cannot pass on this integrity preservation properties. And then there's this nice work by Mary Baker in 2002, which showed that how you can prevent systems that are member of a distributed system, how you can prevent them from cheating or lying about their own states. What they do is to entangle their own states with each other so that no one can lie. If someone lies, the other party can serve as a witness and catch the liar. But again, we are talking about mobile data that gets passed around. And finally, there's this famous work on secure audit logs by Schneier and Kelsey, where they have a model of securing the audit log so that they have a trusted notary who notarizes the audit logs periodically, or start with a hash chain seed and periodically recreate the keys, and so that an adversary can come in and they can generate fake future logs, but they cannot change things that happened in the past. But here our problem is different. Our problem is that the real owner of the document, the real person who signed the document initially, the insider can be the adversary. We're not talking about an outside adversary. We are also focusing on logs on a much finer granularity, not like a single log for the entire system, but sticky logs for each file that get passed along to the file. So in this backdrop, we present our solution for securing data provenance. In our model, we assume that provenance is in the form of a chain. Each entry in a provenance chain contains the actions or record of actions by a user. And each provenance record has this schema. We have the user component, which contains the identity of the principal. Then we have the work log, that is, we have a field where we store whatever action was done or taken by this user in this to modify the document. And then we have some other entries, for example, the confidentiality log. I'll explain each of these fields in the next few slides. We have confidentiality logs field for decrypting the encrypted modification log. And finally, we have integrity checksums for protecting the integrity of the chain. Now, recall that our goal in confidentiality is this. Each user trusts a subset of the auditors, and our goal is that only the trusted auditors, the auditors that are trusted by the user, should be able to see the user's actions on the document. So how do we do that? If there was a single auditor, then the solution would be straightforward. We'll just take the modification log and encrypt it with the auditor's key, and we have this encrypted modification log. We include it in the provenance entry. So later the auditor can come in and use his key to decrypt this, see what happened there. But now we're talking about multiple auditors. So we can use an extension of the same idea. We can take the modification log, make multiple copies, and encrypt each copy with a key of a trusted auditor. And then we end up with these multiple encrypted modification logs. We include all of this in the provenance entry. So each trusted auditor who can decrypt one of these logs can see what happened. But here we are wasting a lot of space. We are including a bunch of copies of the same thing. So our solution is to encrypt the modification log with a randomly generated key, session key, and then take the session key and encrypt the key only with the keys of the trusted auditors, copies of the session key with the keys of the trusted auditors. So now we have this encrypted modification log and these encrypted keys. So each auditor who can decrypt a key can now read the modification log. We can also optimize further. If there are, say, 100 auditors and you trust 60 of them, does it mean we have to include 60 copies of the encrypted key? Well, no, we can use different optimization like the broadcast encryption tree to reduce the number of keys you need to encrypt things. I'll just skip over this slide because we are running a little bit late. So the idea of broadcast encryption is that you arrange the auditors in the leaves of a tree, and each auditor knows all the keys all the way to the root. So if you trust everyone, then you encrypt with this key. If you trust just D, then you encrypt with D's key. And then if you trust B and C, then you use these two keys, their two keys. But if you trust A, C, and D, then for A you use this key, and for C and D you can only use this key to encrypt it. So at the end of the day, for n auditors, you need log n of keys to be included in the chain. So here's again a recap of our solution for confidentiality. We store the encrypted modification log in this W entry. We also throw in the hash of the document so that we can keep a mapping or binding from this provenance entry to that particular version of the document. And we then encrypt this random or session key with the keys of the trusted auditors and put them in this keylog entry. Next, we look into how we can protect integrity. Here our goal is that no one should be able to insert things to the history or remove things and so on. So the solution is straightforward. We take, suppose we are trying to compute this new checksum. What we do here is to take the new provenance entry, hash it, then concatenate it with the old checksum here, and then sign it. So this is the new entry, we hash it, concatenate it with the previous checksum, and then sign it with the key of the current user. So that way, this forms a signed hash chain, so that now no one can remove things from the middle of the chain, because the subsequent checksums will not match. No one cannot also tamper any entries in the chain, because now we use the content of an entry to create these checksums. So if you tamper something, then you can the checksums don't match. Next, finally, we look into confidentiality, fine-grained control over confidentiality. So what I mean is, sometimes you have classified documents that you are supposed to release to public, and these classified documents have secret parts, like this, the parts I indicate here in red. And one way to declassify or release is to redact or remove the sensitive information. You just remove it, or you delete it with black ink and then release to public. But the problem is, what should we do with the provenance chain? If you release the provenance chain as it is, the provenance chain itself might contain secret entries. Now, by looking at the provenance chain, it might be possible for the people, for the outsiders to see the sensitive information. But if we redact these sensitive parts from the provenance chain, we break the integrity checksums. Because now no one can verify the integrity of the chain, because you have modified parts of the provenance chain. So to solve that problem, what we do is to use cryptographic commitments. Now a commitment is just you hash with a random key. You hash, concatenate with a random number and then hash it, and that's a commitment of that original value. So we use it in this way. When we are creating a provenance, new provenance entry, there might be some non-sensitive information indicated here in blue, and then sensitive information indicated here in red. When we are creating the provenance entry, we add this commitment. We take a commitment of the sensitive information and store it alongside everything. As long as it stays inside your organization, it's fine, you keep everything. But also, when we are computing the signature, computing the checksum, we use the non-sensitive portions, and instead of the sensitive portions, we use the commitment. So now we have made it disclosable. Now we make it possible to disclose this provenance entry to outside. When we want to disclose it to the outside parties, we just throw away the sensitive portions. But in the checksum calculations, we did not use the sensitive portions. Rather, we use the commitment of the sensitive portions, which we include here. So now anyone who receives it won't see the sensitive parts, but yet they will be able to check the integrity of the provenance chain. And finally, we have some schemes for summarizing provenance chains. What do we mean by summarize? Sometimes provenance chains can grow really large. Suppose you have a file, small file, say 100 kilobytes, but it's edited frequently. And each time it's edited, an entry gets added to the provenance chain. So after some time, you get a 1 gigabyte provenance chain for the small file. But some events are not really interesting, not important. Maybe you open the file and changed a comma or added a dot, period or something, and that's probably not very interesting. So if you want to remove certain entries from the provenance chain in a systematic way to save space, what do? Recall that we cannot remove entries from the provenance chain because that breaks integrity. So the original scheme doesn't allow us to summarize, but if we change the scheme a little bit, we can do that. So instead of having one checksums per entry, we can have multiple checksums per entry. For example, take say this entry, the third entry from the left. Here, suppose we have add two checksums here. One checksum is calculated by taking the checksums from the previous entry and the current entry and then signing it and so on. And the other checksum is calculated by following this red line to this previous entry, one entries away, and then using that checksum to compute the new one. So what will happen is that now we have provided a way to skip over this second entry to go from the first entry directly to the third one. So now we can remove these entries, but still be able to prove that the third entry is chronologically after the first entry. So it might sound contrary to our original goals. Originally we said we don't want people to remove, but here we are providing a way to remove. So what actually we have done here is to provide a way to systematically remove things from the history. So now an auditor can audit this document, verify integrity, but he will also know that there are some existing holes in the document and where the holes are. Okay. So let's go back to the place where I defined plausibility with all this branching. So what we said there is that using our scheme, we can provide one type of guarantee. If I give you a document and a provenance chain, you can audit it fine. You can audit it and say that nothing has been changed in the provenance chain. But you can't say that this is exactly what happened. Rather, we can only say that this is a plausible provenance chain. This is something that could have happened. Something could have brought the document from its original state to its final state. So we cannot say this is what happened for sure. We just say this is something that could have happened, but there might be cases where this is important. So an easy attack by an adversary would be like this. The adversary just removes all the provenance chain of a document. Maybe there's a famous poem, and then the adversary removes the provenance chain showing the poem was written by Shakespeare, and then adds his fake provenance chain showing it was written by him. He adds a few signatures from a few friends. So the provenance chain is now plausible, but it's not real. It's also not tampered because he included his signatures from his friends. So how can we provide stronger guarantees? We can provide stronger guarantees by entangling the provenance chains of related document. How do we do that? Here's an example. Suppose we have these two documents, the blue document and the green document. And each of them have these two provenance chains, the blue chain and the green chain. Now, an adversary can do this. Adversary can maybe remove this entry and the last entry and the previous entry and add his fake entries here at the end of the chain. So the history is plausible because he computed these new fake entries, but it's not real. However, if we do this, we do a variation of the spiral provenance chain I just described earlier. If we do a variation of that, so rather than entangling a document with itself, we entangle the document with other documents. So here, suppose that in this green entry, we include two checksums. One is computed from the previous green entry. The other is computed from the last blue entry. So now we have made the green chain dependent on the blue chain. So now if you tamper with these two entries, you'll not detect that when you are verifying the integrity of this one, but you will catch that right away when you are verifying the integrity of the green chain, because this fake entry will affect the checksum of this one. It will not match the checksum you have stored here. So in that way, we can entangle a group of documents and have stronger provenance guarantees. Now we can say for sure that this is what happened, because if you create a fake chain, then all the related documents would not match. Their provenance chains and the checksums would not match. And how do we say which document is related? Well, maybe all the babies born on the same date, we can entangle their birth records, birth certificates. Maybe you visited a doctor and all the people who visited the doctor in that particular day, you can entangle their medical records of those people. So now implementation. All this theory is fine, and we have used some existing techniques to provide these guarantees. Okay, that's fine. But is it practical? Can we use it in a file system? So we wanted to check whether we can get good performance numbers, and we wanted to do that in a file system. And there are different layers where you can add that. You can add that to the kernel layer that will be transparent to existing apps. You don't have to change existing apps. You can also add to the file system layer, and finally you can add that to the application layer. So only the particular application that needs provenance would record them. So we chose the last approach. We created an application layer library which we called sprov, and the goal of sprov is to capture file system I/O activities and record that in a secure manner. So this is how sprov works. Sprov captures all the file system calls. So whenever you open a file, do a write, f read, something like that, all that goes through sprov, and sprov now creates appropriate provenance entries and add them to the provenance chain, and then passes off the file system call to the file system directly. And these provenance chain are stored as XML formatted files on the same storage system, or it can be also stored as database tuples. And one of the goals we had is to make it as portable and as easy to deploy as possible. So we provide a wrapper for all the file system I/O in the standard IO.h library. And to have secure provenance in any application, you just use our header files and then recompile, and also change the file system calls to use our file system calls. So I'll just skip this slide to go on to the experiments. So the goal of our experiment is to measure the runtime overhead. So someone from the industry once told me that if any fancy new scheme, security scheme, causes your system to run more than 3% slower, more than 3% overheads, the people will not use it in practice. So we wanted to show or check how much overhead our system would have if you have secure provenance. So we ran a number of different benchmarks, and here's our experimental settings. We used 1024-bit DSS signatures and SHA-1 and so on, and we used two types of benchmarks. The first one is the postmark benchmark, which is a benchmark for small files. The other one is what we call the hybrid workload benchmark, which is a benchmark with realistic file systems and also realistic file system workloads from file system literature. Okay. We also used two modes for storing the chain. In one mode, the provenance chains were stored directly on the disk. In the other mode, they were first buffered in a RAM disk and periodically flushed to the disk. So first, let's see the postmark numbers. Postmark, as I said, is a benchmark for small files, and we created, we ran postmark with 20,000 small files, really small, 8 kilobytes to 64 kilobytes, and we varied the read-write bias, that is the percentage of read transactions. And on the left side of the screen, you'll see the case where all the transactions are writes. And on the right side, you'll see the case where all the transactions are reads, no writes, everything is reads. And we measured the runtime overhead. So at the bottom of the screen, at the top curve, you see the overheads for config disk mode, where we stored the provenance chain on disk. And the bottom, you see the case where we stored the where we buffered the chains first in a RAM disk and periodically flushed them. So here you see that at 100% write load, when all we have is writes, the overhead for config disk is around 27%, and with the RAM disk optimization, we go down to 12%. As we increase the reads and reduce the writes, the overhead goes down, and here the area of interest is actually here 80 to 100% reads, because that's where the typical file system workloads are. We'll actually show that for most typical file system workloads, there's 80%, around 80% reads and only 20% writes. Here you can see that for this real area of where the file system works, we have overheads of less than 5% for both modes. But now there's a problem. Postmark is not a real file system benchmark. I mean, it's not a benchmark for real files and real file systems. In your file system, you don't have 20,000 small files. You have lots of MP3s, lots of videos, and lots of documents with megabytes of sizes, and then also a lot of small files. So we need to simulate what the behavior, test the behavior in a real life file system. And for that, we simulated a file system using the log normal model. People have found that the file size distribution in a file system follows the log normal model. And we created a file system with 20,000 files using these parameters. And because people these days keep a lot of movies, videos in their website, in their disk, we threw in a bunch of gigabyte-sized files. And we also wanted to use data from real systems, the workload. So we used the information from these 5 studies. The first 2 are instructional lab and research labs with very little writes, less than 3% write in both cases. The next are corporate and engineering section workloads from a recent paper, and these are somehow more, but still less than 20% writes in both cases. And finally, there's this weird worst possible case workload, and it has 82% writes, only 18% reads. This is a really weird behavior, but that's the worst possible case people can have. So now we wanted to see the behavior with typical file system workloads and how much overhead we have. So on the left side of the screen, we have the config disk model where we store the files on the disk. So here, and on the right side, we have the RAM disk buffered case, and we varied the number of transactions from I think 20,000, 30,000, 40,000, 50,000, and so on, all the way to 200,000 transactions. So for the first 2 workloads, the INS and REST workloads, you see that the overheads are quite low. Both of these are read intensive. Most of the transactions are reads. So naturally, we are only recording the writes to the provenance chain, so the overheads are low. The overheads are less than 5% here, and here it's less than 1%. How about the next one? The CIFS Corp and CIFS Eng. Well, here, if you recall the previous slide, we had 15 to 17% write transactions in these 2 workloads. But still, we have overheads of around 13% here and maybe less than 3% on this RAM disk buffered case. These are quite low. Even in the worst possible case, in the EECS workload, we have a lot of unrealistically high number of write transactions, 82%. Overhead is naturally high, but we still have around 35% here and less than 7% with the RAM disk optimization. And I also have this slide where we show that even if you record the reads as well, not just the writes, we also tested what happens when we record all the transactions, the reads as well. Even in that case, the overheads are still between 12% to 16%. So in this way, in these applications, through this experience, we showed that it's possible to record all the file system activity in a secure manner, but still pay a very low cost. If you go back to the previous slide, most of the typical file systems behave like these 4 curves, because most of in typical file system workloads, we have more reads than writes, and the read-write balance is around 80-20. So for all of these cases, typically our overhead would be in the range of 1% to 11%. Or maybe 13% here. So now we have, so in this talk I have described schemes for providing a generic scheme for making data history trustworthy in file systems. So that's one way of making data history secure. In the rest, or in related research, which I'm not going to present today, but in related research, we have looked into other application-specific areas as well. And there we have looked into the history integrity problem in databases. That is how we can preserve database history, the history of transactions in a database, and do that with as low as overhead as possible. So we have developed a solution leveraging using trustworthy warm devices, and we incur only 1 to 3% overhead for TPCC benchmarks in databases. And finally, we have also looked into how we can provide history integrity assurances for cloud computing. So now, what can we do in future? That's what we have done so far, but what lies ahead? Now, we are adding more and more power, packing more power into our machines, adding more processing power, adding more storage. Now you can buy a terabyte disk for what, $100 or less than $100. Maybe in 5 years from now, you can buy a petabyte disk for $100. So we have enough space to store the history as much as we want. And we also have enough processing power to process a lot of things. So what can we do if we given enough technology? Well, one thing we can do is to generalize all these things. So we have provenance, we have versioning, snapshots, all these things that are basically a way of representing history. We can call this property remembrance, and we can make different parts of our computing system remember their past. In this work, I just talked about files, but what if your hard disk could tell what it stored in the past? What if your program variables could say, or your program memory could recall what it contained 5 minutes ago? Wouldn't it be nice to have a knob on your machine and go back 5 minutes ahead just by turning the knob? If different parts of your system remembered all their histories, your applications remembered what their state was 5 minutes ago, and your operating system knew, your file system knew, if we could have this common remembrance property, we could do a lot of these cool things. And because this is a security seminar, I'll just talk about what it means for security. We can have interesting things. For example, we can use it for authentication. Rather than using these other factors such as what you have, what you know, and what you are, these 3 factors of authentication, we could have used what you remember. So if someone comes in and tries to get through a door, you can just ask him, tell me what you did inside yesterday. If they can tell you that, then you let them in. So you can apply the same idea for applications or websites or different parts of your computer. Use this for authentication. You can also have flexible authentication, flexible security policies, that is, use the knowledge of the past to make compute complete policy compliance, and also you can check information flow and apply information flow policies based on not the current value but the past values of the variable. So, in summary, we can claim here that we can have secure provenance at a low cost. The message you should take from this talk is that yes, we can have security integrity assurances for data history, data provenance, file provenance, and we can have that, but yet have an efficient working file system. In this work, we show that for most real-life workloads, the overheads are really low. These are between 1% and 15% for typical file system workloads. And if you are interested to learn more or to read the papers, we published a paper in Unix Fast 2009 and also have a journal submission right now. If you want to read them, you can just go to this website, tinyurl.com/secprov, and you'll see the performance numbers from there as well as the papers. So that's the end of my talk. So now I'd like to have any questions. If you have.
Are there any questions?
So let me give you one question. Why can't we take the same technique we used in file systems, and why can't we use it for databases, right? I said that, yeah, for applications you have to use different techniques, different ways. So here's an answer. For file system, you see that the strength of our scheme lies in that we sign each entry and we cannot sign for others and so on. But here we use DSS signatures, and for each DSS signature it takes 1.5 milliseconds. And for each modification you have to add a new signature. For files it's not that bad because we only sign a provenance entry when the file is closed, and that doesn't happen pretty often. But in databases you have thousands and thousands of transactions per second. On an online transaction processing you have a lot of transactions coming in, and if you try to sign everything, remember each signature takes 1.5 milliseconds, so you can't do more than say 500, 600 signatures per second. And that will just kill the performance of databases. So that's why we had to use different techniques for databases. Okay, Chris, you have a question?
No,
Okay.
that's actually what I was going to ask you.
Okay.
Okay.